So in this session we are going to make a rock physics template, and you have been hopefully struggling a bit with some exercising, and maybe some of the threads are still loose. So by this session here we hope that we can connect some of these threads together and build a knot. So when we are going to do a rock physics template, first of all we have to think about what am I going to use this template for? What kind of geology do I consider? Is it a sedimentary rock? Is it a chalk? Is it something else? That's of course very important when you're going to make your template. Also you need to know what is the depth we are considering, what are the fluids, what are the pressures, and so forth. So that's a kind of background information that you start out with when you're doing this pre-analysis. So again, we need to know what kind of lithology, in our case here we are going to look at a sandstone. So it's a siliciclastic system, and we're going to keep it unconsolidated, and it's a basin on its way down. It's under burial. So let's think about that. It's about a depth of 1 kilometer. So we need to know something about the depth. So we say that, okay, this is about 1,000 meters. Okay, that's important information. And as you know, when cementation starts in a siliciclastic system, the sedimentation starts at about 70 degrees Celsius. So we need to know something about the temperature at the target depth. So we need to know something about the temperature gradient of the basin, and of course you should know that if we are in a North Sea system, the change in temperature over depth is about 30 degrees Celsius per kilometer. So that means that at 1 kilometer's depth the temperature is 30 degrees. If it is 2 kilometers, 60 degrees, and so forth. Okay, if you also remember when we discussed about the fluid properties, we need to know the fluid pressure at a particular depth we are considering. So we need to do some calculation of the fluid pressure. Of course, I'll come back to that on the other side here. And we also need to know something about the confining pressure, of course. If you think about these dry rock models that we are going to play with a couple of seconds, we need that there's a parameter here called the effective pressure, which is the difference between the confining pressure and the pore pressure. So we need to calculate some initial parameters here. Also, if you are considering a system where the sediment is under burial, we know that due to mechanical compaction, the porosity is reducing. And then you also have to remember we have a formula coupling depth with porosity of a sinking sediment. So we have to do some simple review of the basic initial conditions. Okay, so let's start with the depth then, and see how the pressure and temperature changes. Okay, so in my system here, I say that, okay, the pressure, as you know, the confining pressure is evolving as rho g set. Rho is the average density of the sediment about the depth point 1,000 meters. And as we have been discussing during the exercising, we very often use a value of 2,000 kilos per cubic meter. So the density is very often kilos per cubic meters. And the reason for putting it like this is from this formula, of course, that the average state density is 1 minus porosity times density of your grains plus porosity times density of the fluid. So if you assume about 25–30% porosity on average above this depth point, assuming a density of 2,600 of the grain, and the fluid is usually water, 1,000 kilo per cubic meters, then you come to a number close to 2,000 kilo per cubic meter. So that's why we say that, okay, we use very often this average number here. So, of course, at 1 kilometer's depth, we could do this, just simply say that this is 10 meters per second squared. That's the gravity acceleration. So we have this kind of rule of thumb saying that with 1 kilometer's depth, the pressure is about 20 megapascal, 1,000 meters. We do the same for the pore fluid, say that, okay, the pore fluid pressure is given by some average fluid density, G and Z. Of course, we could do this by a simple integration where if we have all the numbers in the detail along the depth column, we can do that accurately, but in this case we just use this simple formula, and then we see that at 1 kilometer depth we would have 10 megapascal. Again at 1,000 meters depth. And then of course then this effective pressure is 10. So this is the assumed pressure conditions at 1 kilometer depth. Okay, and then simply enough, as I said just in the introductory sentences, that we have a temperature with gradient dt dz, and then we just multiply, if this is in the change in temperature per kilometer, so we just multiply with the actual depth, and then we are, in our case, at 30 degrees Celsius approximately. So that's important to start out with, because that defines a lot of the parameters you need to know when you're doing the various calculations here. Okay, and then we need to know something about the porosity, of course. We have to have a background model or an initial model And we have this formula that my colleague at the University of Oslo, Knut Bjørlykke, developed, saying that the porosity versus depth depends on an initial porosity. That means at the surface. And then we have an exponential decay, where we have a parameter here, kz, and z, which is depth. But this parameter, this kz, is a parameter that varies with type of siliciclastic system. So if I have a clean sand, this decay factor is different from a pure clay, for instance. I'll come back to that in a second here. But you have been doing some of these calculations, of course, in your exercising. So if I just make a simple drawing here, and this is set, you remember this situation where if, let's say I have a clean sand, well sorted, that means that the grains are same size. They are, in our case, spherical. So for sand at the time of deposition, it's about 0.4. That's a critical porosity. Remember what we mean by critical porosity? If you remove one grain, it loses its share. So it's the maximum porosity you can gain with this aggregate. Okay, so we know that pure sand would about sit down here at the seabed. It's just raining from the sea surfaces and falling into the seabed. It's about a porosity of 0.4. And as it is mechanically compacted, it goes down something like this. So this exponential decay is given by this coefficient here. So this would be for a sand. If I have a shale, we assume that, okay, it has a much higher porosity at the time of deposition, like a house of cards. You can have almost 100% porosity, but the construction is very, very unstable, of course. So shale can flocculate, as we call it, the sea bottom, and then it has a much stronger compaction rate, like this. So at some point, in fact, you can have or you will have a crossover in the porosities of the shale and the clay. So then you can see that this, it must have a different exponential coefficient here compared to the sand. So this is also something we use as initial constraints for making the template. So this is then the porosity. So are there other parameters that we could kind of estimate at this stage? If we think about all these rock physics models, yes, we have one parameter which is called the coordination number. Remember that? It's the average number of contacts one grain has to the order surrounding grains. So we have this simple cubic sphere pack, bunch of spheres, and the loosest packing of them would end up with basically 6 contact points. If you have a hexagonal cubic pack, the average number of grain contacts is 12. And then you remember also that there's a relation between the type of sediment and this coordination number. It's also called the Murphy's law. Of course, we know Murphy's law from other instances, but in this case it means a relation where we can find this coordination number n from the porosity. So this is something we also can do in an initial stage when we are considering a sediment. So I did some pre-writing here. So you can see here, it's the same as you have in your manual. And you see that, okay, if I have well-sorted grains, I have this relation, and it's a second order equation in porosity here. So this is for well sorted and poorly sorted, and then we have one for angular grains. That means that they are at the same size, but they are kind of flattened and they have some more edgy shape. So this is something that we have as a background when we are now going to start making the template. So I will go back and look at some of these equations as we go along. But I don't need to know any rock physics in order to do what I have been doing so far. I'm going to leave it here, and then I'm going to put it up later on. Okay, so far so good. Now I'm going to start using numbers related to the rock itself or sediment itself. So of course, when we want to make a rock physics model, we want to establish a system of different minerals and fluids, and then finally compute the seismic properties, bulk modulus, shear modulus, Vp, Vs, density of this whole system. So let's start by picking some minerals, some fluids. So the first thing we start with is to pick the constituents. So, okay, let's start with a quartz. We want to have a siliciclastic, so we have a mix of quartz. And we have some clay. We have water. We have oil. And we have some gas. So these are the components that we want to mix. So of course we need to define the individual properties of the various constituents here. So of course we need to know the bulk modulus, the bulk. Okay. We need to know the shear, mu, and we need to know the density. So you know that if you look into the rock physics handbook, or I even have a table in your manual listing up different values for quartz, clay, feldspar, and so forth, different clays. And we know that basically the elastic moduli are in the range of 10 to the 9th Pascal. So usually we just define them as in gigapascal. That goes both for the bulk and the shear. Our density is kilo per cubic meter. So for quartz, it's 36, so it's a relative stiff material. Specific things about quartz is that the shear modulus is even higher than the bulk modulus, and that is very imperative for the final result. So you should kind of see this in particular, that you're raising the elastic modulo from the bulk to the shear. Density is about 2650 here. So that's one of the pieces we're going to put together here. And then the clay. Clay is a kind of difficult mineral to define, and there's a lot of published papers about the properties of clay. Some are related to clay with bonded water, some are with dried clay, and so forth. So you should always be careful when you look at the clay properties. In our case, we are going to use some well-used clay properties. It's from clays in the Mexico Gulf, defined by hand. In a paper 30-40 years ago. So it's a bulk of 21 and a shear of 7. And look here, compared to the quartz that you have, the shear modulus is almost 1/3 of the bulk modulus of clay. But it's almost a similar density as quartz. So this just tells us that using density to discriminate quartz and clay is not very good. Best way to discriminate between quartz and clay is through the shear modulus, but still there's something left for the bulk modulus. Okay, and then the fluids. Okay, water. What do we know about water? Yes, it's almost, it's quite a stiff, stable fluid. And if you think about some of the presentations I had, I think it was yesterday, we say that the water depends on its salinity. So we need to know its salinity. But of course, pressure, the pore fluid pressure, is important, and of course the temperature. So we need to use these parameters when we want to define the elastic properties and density of water. And I know that you are a member of the FLAG consortium, or I don't know if it's called FLAG anymore, but it's a consortium at the University of Houston, where they have for many, many years calculated and measured bulk, density, and viscosity of various types of fluid. And the first paper, an important paper on this stuff, was published by Mike Batzel in 1992. So using their basic relations, we can find the water properties for the specific reservoir conditions. And now, for simplicity, I just use some average numbers. So I will use 2.4 here. Density is 1000, and the shear modulus is, of course, vanishing. It's no shear in fluids. Same with oil. In this case, I need to know its reference density or its API number. And again, both the pressure, fluid pressure, and temperature. And basically it's softer than water, so let's just use this number 0.8. It's in the range, and the same here for the density, just for simplicity. And it has no shear. Gas, same way, you need to know its gas gravity. It's a very light gas. It's about has a number of 0.6. You may remember that. And if you have a heavy gas, it has a reference value of 1.2, I think. But again, you need to know both the pressure and temperature. So gas is basically 1 to 2 orders of magnitude of lower stiffness than water, so it's much, much softer. You know that for taking a balloon, if it's filled with water, it's difficult to compress. You can deform it, but it's difficult to compress. But if you have gas, you can for sure just shrink it quite easily. And also, the density is much less. So these are the bits and pieces we want to put together. And I just want to emphasize that in order to find these parameters here, you use the FLAG software. These values you find in any rock physics handbook. Okay, so now we have picked up the bits and pieces we want to put together in different ways. So we have all the bits and pieces, and now we're going to put them together. Okay, so if I want to start with mixing quartz and clay, we need to apply what we call some mixing laws. So if I put together quartz and clay, no porosity in between, I just make a new stuff with quartz and clay where I distribute quartz and clay in a different way. You know, of course, that the composite elasticity will be different. You can have a soft mix, you can have a stiff mix, you can have an intermediate mix. So we know this as, for instance, the Royce mix, which in fact is the softest possible way of mixing. This is also called the arithmetic average. So if I have a quartz, let's just call this KQ, just so we know that when I write KQ, it means the bulk modulus of quartz. Kc is the bulk modulus of clay. UQ is the bulk modulus of quartz. And mu c is the bulk modulus of clay. Okay, so back to this. If I mix quartz and clay, the softest way to do that, I can find what I call average or composite bulk modulus of this mixture. And that would be the amount of quartz divided by this bulk modulus, and the amount of quartz. If I say I have a clay fraction C, the quartz fraction would be 1 minus C if I just have two solid components, plus C over K clay. So that's a way of finding the softest possible model. And the similar way is for the shear modulus. So if I start mixing them, this is the soft one, and then we have the stiffest in fact, which is called the Voigt. Mix, which is Ks equals to 1 minus C times bulk modulus of quartz plus C times bulk modulus of clay. US is 1 minus C K U Q plus C U Q. So then we use some kind of mixing model. Very often you don't know how they mix. Some parts within the microstructure is softly mixed and the other one is stiff. So very often we use this Hill average. Which just say that Ks, so in order to separate between the different mixing models, we used to put on a R here to show that this is the Royce moduli and this is the Voigt. So the Hill, Ks Hill, is then just taking the two moduli K stiff one and the soft one, say with US. As I said, this is sometimes called the harmonic average, and this is sometimes called the arithmetic average, and that is defined by this averaging procedures. Okay, so I can mix the solids in different ways, so I just have to pick one model. What do I believe? And of course, this is an interpretation exercise. So what I would usually do is that I would pick the Hill to begin with. If I got some information of particular interest, for instance, if the clay was pore filling clay, then I could use another model. I could use the Herschen-Strickman, where it had a stiff shell surrounding a soft matrix. So then I could use the Herschen-Strickman models. Then you have to go back to your manual and look at what was defined about the Herschen-Strickman. If I had a clay coating surrounding a grain as the main picture of this mix, I would use a lower Herschen-Strickman bond. So there are kind of many ways to roam. There are 5 very often used models: Royce, Voigt, Hill, and then we have the Herschen-Strickman models. I'll come back to that in a second here. So here's the Herschen-Strickman, and again you see that it's basically the same parameters entering here. It's the volume fraction of, in this case it's the lower bond, so then we have a soft coating of a stiff shell, a stiff core. And you see that's more or less the same parameter, or it is the same parameter. It's the elastic modulo of the two components, and it's the volume fractions. But it's one small difference here, is that the bulk modulus using the Hershey-Strickland bounds also involves one of the shear modulus. So there's a coupling with the bulk and shear, which is not in the other two models, or the other three models, I would say. Okay, I'm going to use this later on, but we could use also this model to mix the two solids. Okay, so 5 ways of mixing the quartz and clay. Stick to the heel when you start your template making, and just try other models if you want to later on. Okay, so what about the fluids? Now I've been mixing solids. Of course, we have a same way of mixing fluids. So if I have a fluid I want to find, if I have two fluids, I want to find what I call the fluid bulk modulus, would, in a similar way, would describe the composite bulk modulus of the two mixing fluids. So when it comes to the fluids here, we have the three fluids could have different saturations here. So I have the saturation of water, saturation of oil, saturation of gas, which just individually defined the volume fraction of the porosity occupied by water, oil, and gas. So, of course, when you add them together, they always add up to 1, or should add up to 1. So if you're making your own script, doing some rock physics, before the code starts, you should always assure that the various components adds up to 1. So for the effective bulk modulus here, it would be, in this case, the volume fraction of water defined by its bulk modulus, which is this one. K W for water, K O for oil, and K G for gas. So it's just the sum here. Usually we, and as we are going to use in the template I'm going to make for you, is that we just consider water and gas. So we pick the stiffest and the softest components here, and then we know that the oil would be somewhere in between the two end members. So in our case, we will define the gas saturation, and then we know that the water saturation is simply 1 minus Sg. So when I compute the effective bulk modulus, it would be 1 minus Sg divided by the bulk modulus water plus Sg divided by the bulk modulus of gas. And this, of course, you see that this is the Royce average. It's also called the Woods equation. And it defines the bulk modulus of a homogeneous mixing system. Okay, so now we have emphasized how we can find the what we call the solid bulk modulus, the solid shear modulus, when we do a mixing of these minerals, and also showed you how we can find the bulk modulus of a system of 2 or more fluids. In fact, this could count up any number of fluids as far as you know the volume fractions of each of these fluids. Okay, so let's see what this really means for these elastic properties, because if you have this as a background, you can go and recalculate your template just by another do loop. So I'm just going to make some simple drawings here. Okay, if I say that, okay, this is the bulk modulus for the solid, and this is the clay fraction. I would do the same for the shear modulus. And the density. So I have US and I have rho S. And finally I have also for the fluid, the bulk modulus of the fluid dependent on the saturation of gas. So in this case I look at the clay fraction for the solid part, and for the fluid I use the saturation of gas. So let's start with the first one here. Of course, when there's 0 clay, I have a value here which is simply the bulk modulus of quartz. So it's 36 in this end, and a clay fraction of 1, well, then it's 21. So it's here. So if I use the soft mixing, the void mixing, it will go something like this. So then I can find the bulk modulus for any clay fraction with a softest possible mix. Softest. If I do it in the stiffest way, I do the void, and it's just a linear change. This is the stiffest. And finally the hill is just something in between here. Okay. So that would be the average. And if I use the upper Hershey-Strickland bond, in fact, I would find something in between here. Like here. So that would be a Hershey-Strickland upper bond plus, and in between here it would be the Hershey-Strickland lower bond. So you see that the void and Royce represents the stiffest way of mixing two solids in an isotropic system. If I do the same with the shear, you can see that the shear would be very high for quartz 44, and for a clay fraction of 1 it would be down here to 7. Worth noticing now that, okay, the contrast between the elastic properties of the shear moduli is larger than for the bulk. So the choice of mixing model becomes more significant. So you see that if I use a soft mixing model, it would be something like that, and the stiffest, something like that, and the average is somewhere in between here. I don't care about using the Hashing-Strickman upper and lower bound because it gets too messy here. But my point is here, if you then go at, let's say 50-50 mix, you see that there's a variation range here, which in fact depends, if you look at the elastic moduli here, it depends on the type of geometry of the mixing that you assume. If you do the same here for 50-50, you see that this range is much larger compared to that one. So here we see the role of the mixing. So if the contrasts are almost zero, if this was 36 and the other one was 30 or 32, or you don't have to care about the mixing model. You could use any mixing model and it would hardly impact your final result. But that's when the contrast between the components you have a large, when you have to be a bit focused. Okay, for the density, well, for shale, sorry, for sand, it's about here, 2,6, 50, and it's 2,6 here, so it's almost straight line. So, and it's important to see that, of course, for the density don't care how the constituents mix. It doesn't affect the total density. But for the elastic moduli, for sure, the geometry of the mixing is important. And then we have the fluid properties. For zero gas fraction, it's 2.4 here. So it's 2.4 here. The other end, at fully gas saturation, it's very low down here. So then you see that it's quite some contrast, and if you use the Royce or Wood model, it gives you a change like that. Worth noticing that just a few % of gas into water makes a huge effect on the fluid bulk models. So these are background functions that we will now use. So it's easy to go back and update our model just by picking values here, as I will show you. Okay, so now I want to get some porosity into the system. For now, we've just been mixing the solids for themselves and the fluids for themselves. So we need to now find the elastic properties with some porosity. And that's when these Hertzsch-Mindlin models, contact theory models, and other models, Walton model, for instance, comes into play. So the next step now is to start imposing the depth in terms of porosity. So let's go over here and say that, okay, next step now is to find the dry rock properties. Dry rock, if dry means something, it just says that, well, you have a pore space which is dry, there's nothing inside. So for a while we can just forget about the fluid here. So if you remember some of the from the manual now, and you know that, okay, the dry rock properties they defined the frame, the elasticity of the rock, the porous rock with no fluid inside. And of course it depends on the porosity. It depends on the bulk modulus of the solid. So now we have kind of converted a mix of different solids into one solid. So the mixing of the various solids is hidden in this parameter. So we don't need to have all these solid properties. They are hidden into this solid bulk modulus. And the same with the shear modulus of the solid. Okay, and then we need to know the effective stress, you know. The stress that acts to compact the grains. And that's, you know, the fluid pressure acts in the opposite way. It would like to displace the grains apart, while the effective stress is the difference between the confining stress and the pore fluid stress or pressure. And then, if you remember, there was a coordination number here, or N. So we now need to find the porosity, and that's what we did initially. We used this formula to begin with here. It's still here. So we could, if we have a sand and we have defined a porosity of, let's say, 40% here, and we pick the correct coefficient here, we can find the porosity at 1,000 meter here. So for simplicity, we just say that, okay, we assume the porosity is 40% according to our formula here. Or let's say it's 35. That's 35. We said it started out with 40. It's decaying, so it's about 35 at the depth of 1,000 meters. So, okay, we know this. It's 0.35 according to our formula here. Okay, we pick, then we have to pick a mixing here. I could pick some K fraction here and find the Ks, and the same with the µs. But let's just start out simple here and just pick pure sand. See where pure sand will show up in a rock physics template. So I use this for Ks, and I use this for µs. So then this is the same as it's 36, and this is 44. And then this is, you remember, confining stress about 20 megapascal, pore pressure 10 megapascal, the difference would be 10. And then next, the coordination number. Okay, if we start out with a well-sorted sand, so well-sorted sand, I know the porosity, 36 here, 36 here, number pops out here. So I know all the parameters here. So now I can find the dry rock properties simply by assuming that we have a system described by Hertz-Mindley. It says that, well, we have an unconsolidated sand. The dry rock properties is given by the following. Yeah, again, I have the coordination number, I know. I have the porosity. It's a critical porosity, but it's just a critical porosity was set to the surface of 40%, but it's extrapolated down to 36 here. So we know this. We know the shear modulus. And what is this? It's the Poisson ratio of the grains. The Poisson ratio of the grains are just given by this simple formula. So when you know Ks and Us, you find this Poisson ratio. And that's the reason why they use the Poisson ratio, is just to make this formula a bit more compact. So we know the Poisson ratio of the solid here. And again, these are 36, 44. And then we also know the effective stress. So now we can start computing the dry rock modulus for this depth, for this well-sorted sand at a specific porosity. I cannot calculate as a function of porosity, but just for a specific porosity at this depth. Of course, we know that the porosity at 1 kilometer depth is not constant, equal to, for instance, 36%. That's also due to sorting and lithology and so forth, but we'll come back to that. That's a kind of a idealistic point, and we are going to interpolate from that one. So, and we see it's the same parameters that we have over here for the shear modulus. Coordination number, porosity, shear modulus of the grains, Poisson ratio of the grains, and effective pressure. So it's just two formulas. So now I would like to make a plot of what I know up to now. I have the bulk modulus here. Dry bulk modulus versus porosity. I have the dry shear modulus versus porosity. And of course I have the density of the dry system versus porosity. And now I'm at a particular depth of 1,000 meters. So I say that the maximum porosity I can have at this depth of a well-sorted, unconsolidated sand is 36. So I could limit myself to 36% porosity. Okay, so if I use these two formulas here, I would obtain what I call the dry rock modulus lying about here. Maybe I should first of all plot the data point at 0% porosity. What would it be at 0% porosity? Well, it's just a mineral point. We call that the mineral point. And the mineral we have here is quartz. So at 0 porosity, it would be 36. I know that. So this point here points directly to that point. That's my peak here. And same here for the dry. This points directly to this one. So if I had selected another situation here, let's say a 50-50 soft mix, that would be my starting point. That's my solid mineral point. But in this case, we are looking at pure sand. Okay, I use this KS and US and end up with this point here, which I call the bulk modulus using the Hertz-Mindlin theory. We call that the Hertz-Mindlin point. It would be approximately the same here for the shear modulus. However, the density is very simple to calculate here. I could just use effective density 1 minus porosity times density of the solid. And of course, our solid here is 2.65. So it's, since we have no fluid, it's just one simple line here. So it would be down here, and the other point is up here, 2.6. And we immediately see from this equation that the dry rock density would just be a straight line like that. Okay, so the density is, this formula is the most exact rock physics formula we have, because this is just how the world is. So we can interpolate here because with the porosity, it's a linear relation, so we can see that there's just a straight line. It's not that easy to interpolate between the mineral point and the Hertz-Mindlin point. But of course, we can use some of the mixing models we have used before. You could argue that, okay, why don't you use this Hertz-Mindlin model? If you change the porosity here, you could, in fact, update the coordination number, but then it would follow more like Roy's model. But that's not basically how we do it. But just be aware of that. That could be an option. But we are going to be a bit more flexible on the way we are interpolating here. Okay, so I need to interpolate the dry rock properties here. Okay, so of course we can go back to our mixing laws of two solids. Just as we mixed a stiff quartz mineral with a soft clay, we could do it in a stiff way, soft way, intermediate, or I could use a Hashing-Strickman. So I can reuse my mixing in order to mix my stiff end member with my soft end member. And that's what we usually do. And now we can kind of add some geological interpretation to our choice. Remember this soft sand model? We have already discussed that, and that just means that, okay, if I use a Hashing-Strickman lower bound, I'm in fact trying to reduce the porosity by poorer sorting. So I'm just copying this bulk modulus over here. We had a porosity of 36 here. I had my Hertz-Mindlin point here. And then I have my, this is the K dry. And then I have my mineral point of 36 here, okay? So now I can start mix these two. Let's just say, what is the porosity if you're mixing two end members here? Okay. If I have a volume fraction of one material with porosity 1, and I have another materials with volume fraction V2, which in our case just would be 1 minus V1, since we just have two components here, phi 2. So if I mix two end members, and of course this is simple because the porosity is 0 here. So we see that the total porosity is simply V2 times phi 2, which is 0.36 in this case. This is the end member. So then we know for any porosity here we want to interpolate, we can find how much of V2 we need. So what this says is that V2 is simply porosity divided by phi 2. So when I know the porosity at this point, and I want to do some averaging, giving me the value at this porosity anyway in between the two end members, I can find how much of V2 I need to add in my mix here. Okay, so it's easy to find how much you need to mix of the two end members in order to arrive at a certain porosity. So then I could use, I said, any mixing model, but in here we assume that, okay, we have perfectly sorted medium here. That's the interpretation of the Hertzsche-Milling point. If I use the Hertzsche-Strickman lower bound, and this is unconsolidated, I could kind of try to interpolate somewhere in between here, saying that, okay, I end up with a less well-sorted stuff. And that, if you see the cartoon of the rock for the lower Hertzsche-Strickman bond, it's a kind of mixed size properties here. So in this case, we just have quartz, so of course we mix a large grain here with a set of smaller grains here. So that's the interpretation here. So I can, in fact, interpolate using the lower Hertzsche-Strickman bond. And I showed it you to begin with here. I just need to find it. Here. Here it is, and I just have to keep my mouth straight in the mouth and see what kind of parameters I need here. Okay, K2 is the softest one, so this would be associated to the K dry Hertzsche-Milling point. This would be the mineral for quartz, KQ. And again, K2 is known here. It's the same as here. And then the shear modulus here is the dry shear modulus at the Hertzsche-Milling point. V1, yeah, it's 1 minus V2. And if I just pick some porosity here, I would like to find the value here at, let's say, 10%. Yeah, okay, I say that I defined 110, and I know the porosity here, it's 36, and then I know how much of V2 I need to add in to arrive at a porosity of 0.1. So then I find the V2 here. And then I have all the parameters here. So I can start interpolating for each porosity in a small intervals as you would like to. So if I use the lower Hershey-Strickland, I would be able to draw how the porosity affects the dry rock bulk modulus from a Hertz minimum point back to zero porosity, the minimum point. And that would go all along here. So now I have the dry rock properties for any porosity at this depth, where I have used consistently all the information that are available at this stage. I have no wells, I have nothing else than some assumptions about the system. Sand, perfectly sorted, on its way down, buried. Okay, so what's next? Yes, I need to add the fluids inside. What is the effect of the fluid? Okay, for the, let's say we had a water-filled system here. If I have some fluid here for the density, look at the density first. If we have water, I have 1,000 kilo per cubic meters. I can, of course, find this. It's still a linear equation, so with water inside, it would become a bit denser, so the density would increase. Very simple. The only exact rock physics equation we have. What about the other one here? Yes, that's when we do what we call the fluid substitution, using the Gassman equation. And you know, some of the difficult things about using the Gassman equation is that we need to know the dry rock properties. And the dry rock property is something we can measure in the lab, for instance. But now we have a system which gives us the dry rock properties as a function of porosity. That's what this do. So I have the Kd as a function of porosity. Okay, so I now need to do some fluid substitution. And the Gassman equation is here, the Gassman model. So in order to find the total bulk modulus, when I have some fluid inside here, here's the bulk modulus of the fluid. Here is the dry rock properties, here, here, and I also have the fluid here. And then I have the bulk modulus of the solid here. Okay, so when I have a sand, this was 36, 36, 36. The Kf, okay, if I first of all just consider pure water, so let us start with this one, pure water. Here, that's 2.4. So Kf is 2.4 here. Yes, 2.4, 2.4. And now we can just change the porosity and the dry rock, because we know the correlation between the dry rock and the porosity. We have it here. We have it here. So now we have all the parameters we need to predict the bulk modulus when we saturate this with, to begin with, water. Shell modulus, well, doesn't care about the fluid inside. That's one of the important issues of the Gassman equation. So I can just do that. So what happens here? Well, when I add some fluid inside here, this point would just go up here. Large porosity, large fluid effect, and so forth. I can just take the KD and porosity and plug into the Gassman equation, and then finally I would end up with a fluid effect like this. Fully water saturated. The shear modulus unaffected, so I don't have to care about that one. And now I can start adding different fluids or different saturations. So let me add 10% of gas here. Okay, what does that mean? I add 10% of gas, that means that the bulk modulus here of the fluid would change. I can't use 2.4 anymore because that's for water. But I have my relation over here. So let's say I add some 10% here of gas. And then you see that the Kf is jumping quite a lot. Maybe 1.9 or 1.5 or something. It's almost half here. So if I add this new number here, I could use a red. Just say then, okay, then this becomes 1.5, 1.5, and I do the same here. I would see that, okay, I had a huge drop here, it would move up here. And if I did it for every porosity value here, it would be up like that. So the blue one here is 100% water. While the red one is 10% gas. So you see that due to the harmonic shape of this one, huge effect of gas to begin with here makes the bulk modulus to lower very fast. Makes a huge effect here. So just by adding a few percent gives a large effect, and then as you add more and more gas, you see the steps becomes smaller and smaller. So with 100% gas, I probably have a line that's just very close to the dry rock down here. And that's why seismic is kind of a bit difficult in reservoir monitoring, as you, in the last stage of the injection process, when the gas content exceeds some certain number, there's very small effects on the bulk, and even less on the shear. But of course, the effect of the gas separation is linear when it comes to the density here. So it would go in equal steps here. So the gas would, 10% gas would be about here, or 100% gas would be a bit larger than the dry. So we'd have a different jump in the bulk with small parts of gas here and very small here. Okay, so we have reached quite far now, because now we more or less have all the values we need to make the final template. And we have, I would say that, okay, the K dry is only associated with the white line here. Now the curves with the colors here are a dry rock that's filled with some fluid. So I could maybe say that the green here means the bulk modulus and shear and density with the fluid inside. So for the colored curves, it's the total bulk modulus. The white one is the dry modulus. So now I can just, if you think about an isotropic system, I have Vp, which is k plus 4 over 3 mu divided by rho. That's the p velocity. Vs, it's mu over rho. So now I can just start by systematically sampling these curves, combining with the same points of the other parameters and find the Vp and Vs, and I can of course find the rho Vp and Vp Vs or whatever you would like to. In our template, I would like to use the Vp Vs versus the acoustic impedance as we have been reviewed before. But of course you can, when you know k and mu, you can of course make yourself the rho mu and rho lambda. Lambda is just k plus 2 mu or something like that. You can find mu from k, lambda from k and mu. So you can make any kind of template. But let's stick to Vp over Vs versus acoustic impedance. So Vp Vs versus acoustic impedance. P wave impedance. Of course you could use the S wave impedance if you would prefer that. But it's quite simple now. What I start out with now, I would like to see how Vp Vs would relate to acoustic impedance for a water saturated sand. So that means that, okay, I start with this one. So I would like to sample the points here for every 5% porosity. Just sample this curve. And this one as well. With this one, the blue one, water saturated density. Okay, so I've just used this string some numbers, combined it with these simple formulas here. So let's start with this one, combine these three values, which defines the mineral point. And the mineral point would be about here. Has a very low Vp-Vs ratio of quartz because the shear modulus is so high compared to the bulk modulus. So it's lower down here. You would have a number about 1.6 here. That's what we call the mineral point. Okay, so if I'm just taking that point, combining with that, and so forth, and then next one combining with so forth, I would see that I would get this combination of the three lines would go something like that. So at this point I would have 0 porosity point, 0 porosity, and at the end point here I have 0.36 porosity. And then I have for each 5% maybe something like that. So that's the water. So we see that, okay, with the increase in porosity, clean sand, I would have maybe a slight increase in the VPVS. So what happens if I then use the 100% gas and do exactly the same, just sampling the points along the lower red line here and combine it with the similar points as before along that one, and then use the lower red line here. If I just combine these three lines or curves, input to these two simple formulas, gives me a red line here. It's going down here, something like that. So the 1.6 should be maybe a bit lower down here. So what we see is that the effect of increasing porosity with a soft gas inside would make the VPVS to drop and even get a lower acoustic impedance for the same porosity. Of course, we know that since the density of a gas-saturated system is lower than VP, so we see that this is reasonable, that this point goes further to the left of the blue line here. So this is the porosity point with 36% gas. Drop in VPVS, drop in acoustic impedance. And then if I use the 10% gas line, I would have something ending up like that, about. So this is 10% gas, 100% gas, and the blue one is water. So we see that the fluid effect here for the same porosity is quite dramatic when it's come to the VPVS. It's lowering the acoustic impedance, but it gives a larger effect on the VPVS. Okay, so this is the template in case I use a clean sand. If I did the same, just say that, okay, I assume, let's say, a hill mix here, which is the line in between here. Midline, I can make it even red here. Same here. Then, if I did the same as we just have done now, and then I would see that my mineral point would move. So this is clean sand, remember? My mineral point would move in that direction, away. So if I did the same just with the pure clay over here and here, I use the 7 for the shear modulus, 21 for the bulk modulus, and then you see that, okay, with a very high bulk compared to a shear, I would have a high VP-VS ratio for the mineral point. And that's exactly what happens. The mineral point would increase quite a lot. And if I don't just, again, did the same, I would see that, okay, my shale, water-filled shale would move up like this. If I filled some gas into the shale, it would move something something like that. So we see that, I used to call this the mouth, open mouth, where it's closing dependent on the type of fluid. So if you have water here, the gas here, and you get oil inside, it's closing a bit. So oil represent properties in between the gas and oil, so we know that oil points would plot down here. But this is how a shale would move into this. So we see that the shaliness would move the points in that direction. So if I've here, if I have pure sand and it becomes more shaly, I expect it to move in that direction. So now I can start imposing some interpretation rules of thumb into the system here. So if I say I have a clean sand here, I'm about relative high porosity sand here. Here's my reference point. If I'm increasing the porosity, let me make the green one, just the green. If I'm increasing the porosity, it moves in that direction. So that would give me the porosity trend, increasing porosity. So we see you have an effect, an acoustic impedance, maybe a slight effect on. At least you're moving to the left here. If you have if you're down here and increase the porosity, you can even have a lowering of the VP/Vs. So you always have to think about where you are in this plot. But basically it moves in that direction. If you're increasing the shaliness, or you go into a more hydrolytic sand, basically it moves in that direction. So this is increase shaliness, or shale, increase porosity, and then you have the fluid effect here, which you can call the hydrocarbon effect. And then I could also have shown you what happens when, for instance, I'm increasing the pore pressure. Let's say I had an anomalous pore pressure, not given by this simple equation, but I was increasing. What would happen then? Yes, with the dry rock properties, it would make the system looser. So the elastic properties would be reduced. So in fact, the effect of increased pore pressure would also move in that direction because it's looser. Okay, so this is how you make a template. It's a bits and pieces that needed to be put together, but this gives you the roadmap. So in a minute, I'm going to show you what happens if it starts to consolidate. Okay, so what happens when we move deeper down to, let's say, 2,000 meters? You already know from your exercising, but I would just emphasize how we need to update these rock physics templates. So first of all, we know that according to the porosity would be reduced. Think about this mechanical compaction, and when we start to cement, we also start with chemical compaction. So if you think about the involvement of the porosity, if we have the porosity here, depth here, you know that, okay, porosity would reduce like that, and at some point here, 70 degrees Celsius, it starts to become chemically compacted. It starts to form cement inside, in between the grains, and then it ends into the pore space and reduces the porosity. So dependent on the temperature gradient, the porosity would have a bit different trend dependent on the, I said, the temperature gradient. So let's say we are down here somewhere. So we have had added on some cement. Previously we were maybe about 1,000 meters. But of course about 2 kilometers, that's approximately where cementation starts. So in our case, if we just say that we have passed the cementation depth level, so we start getting our rock cemented. I just cleaned up some of the drawings, but I have some reference here just for you to know. We go back here. I had the Hertzsch-Mindlin point here. Here for the bulk modulus and for the shear here. And then I did this interpolation using the lower Herschel-Strickland point. So these are the dry rock properties at 1 kilometer depth. Density would behave almost the same, so I will just let it remain as it was. Of course, when we start compact, we have a reduced maximum porosity, so you just need to compute for a lower porosity range. Okay, so I also just left with the template in case of a water-saturated sand, 1 kilometer depth, and in case it's gas-filled. So the procedure is, in fact, very similar to what we have been doing. So I don't need to review what we did about the mixing of the solids and fluids, etc., etc. The only piece we now need to reconsider is the model for the dry rock property, because in this case it's unconsolidated sand. So we need to find another model to compute dry rock properties. And we have already discussed it in our exercising and our presentation in the manual. So we can now use consolidated sand or the contact cement model, contact cement theory. Very often it's just given by the CCT, constant cement theory. The good thing about it is that it's evolved from the Hertzsch-Mindlin model, so we have more or less the same parameters. So we have the coordination number, we have critical porosity, and then we have the what we call the M moduli. It's an elastic moduli of the cement. So now we need to know what kind of cement you're filling in between the grains. So very often we use quartz as cement, and of course then we use the elastic properties of quartz as cement. So I could just define that, okay, this M modulus is just simply the K, the bulk modulus plus 4/3 times the shear modulus. And if you see in this formula here of the VP, it's just the numerator of the VP formula. So we all very often call this a plane wave elastic moduli. So it's just, so we see that we also need to know the bulk modulus of the cement. So if it is quartz cementation, it's 36 here and 44 here. If you use clay, we use 21 and 7. So, and then we have what we call the normal stiffness and the tangential stiffness. And those are the parameters that depends on both the amount of cement, which we call the saturation of cement, just as we say saturation of water or gas or whatever. When we say the saturation of cement, we define it as a fraction of the pore space that's now made up by this cementation process. And then I need the Poisson ratio of the grains, just as before, the shear modulus of the grains, and then the shear modulus of the cement. So these are some formulas that's given in your manual. I don't show them here. Only thing to notice here is that moving into a contact cement theory, you have to have some idea of what kind of cement you have and the amount of cement. Another thing that is kind of a bit strange here is that the pressure dependency is no longer visible. It doesn't show up in the equation. So this effect has been debated. Why are the pressure effect absent now? Because if you look at the Hertzsch-Mindlin model, we needed to have the effective stress. We're later on going to discuss about what we call the patchy cementation model. And that's one way of including pressure into the system. But that is going to be discussed in another setting. Patchy cementation model. Okay, so what happens if I go back to my curves over here and say that, well, I have put some cement, quartz cement, into the system. What would happen? Yeah, I have my Hertzsch-Mindlin point, and then I add some cement. What happens? Okay, with the increased cement, I reduce the porosity, and we know it's stiffening the rock quite a lot, so this would jump up here. So that would be my dry rock modeling for a contact cement model with, let's say, fraction of 1% cement. If I add 2% cement, it would jump up here, 3% and so forth. So the steps would be smaller and smaller if you increase the amount of cement. Just like as when we add a gas into water. Look at the bulk modulus here. How it changed with water, adding gas, we saw that it dropped, but as we increase the amount of gas, the drop is decreasing. So that's what happened with both the bulk and the shear. So this point jumps, so that's now the maximum porosity point. So this would be the mu CCT. With 1% cement. And basically, that's what you usually do. You just recalculate, instead of using the Hertz-Mindlin, you use the contact cement model. And then it's a matter of taste, but some like to use the upper Hertz-Strickland bond now, because it's kind of mimicking that we have a shell of a stiff material, the stiff quartz cement, which is sheltering the softer clay inside. So often we, instead of using the lower Hertz-Strickland bond, we use to have a upper Hertz-Strickland bond. And same here. So it should maybe go more like this. But you could, of course, argue if you are using a clay as a cementing material that you would like to use a lower Hertz-Strickland bond, because you think that the clay is then becoming a phase that is surrounding some of the stiffer grains and so forth. So basically, this is the effect. Now I've exaggerated the effect here. It should, in fact, have been a bit smaller here. So it maybe should be down here. So the first percent is down here, same here, because otherwise I lose the fluid effect here. So something like this. Okay, so instead of using the Hertz-Mindlin porosity line, I now have a contact cement theory porosity line for the dry rock properties. Okay, so with a new relation between the dry rock and the porosity, I just insert a new set of relation into the Gassman model. So again, I start filling my endpoint here. Let's use the blue to be consistent here with water. So I have a water setter line here. No effect on the shear modulus according to Gassman here. It says that, well, as long as you know the dry rock properties, water does not play any role into that. And then we have the fluid that just follows the same trends or lines as before. So I can do the same for the using the gas, and it would be just, of course, hardly move up from this dry rock line. Okay. So then I can start comparing what is the effect of cementation to my unconsolidated sand. So I can use the same plot here. Okay, the mineral point for quartz is the same. You always start out here. That's the mineral point. If I follow this line, you can see that the VP over VS is changing. So what I would get here is something that follows here, ending up here. And if I have gas, it would go something like that. So the effect of adding cement into the system is losing the gap. The smile becomes less. The mouth is closing. And of course also the fluid effect is reduced compared to this one. You see that the change in the VP over VS and also the acoustic impedance becomes less when cementation is present. And of course, that's the container. As the sand becomes stiffer, the container is less compressible and it's more difficult to feel what's inside. So altogether, we can say that, if we just summarize once more, we have a porosity effect. Increasing porosity would move a point in that direction. If we are increasing the cement or consolidation, we are moving in that direction. If we are increasing the hydrocarbon content, you increase the gas saturation, we are moving in that direction. If we are increasing the clay content, we're moving in that direction. So now we see we have some kind of rules of thumb. There's not orthogonal effects, but because there's just some arrows here. And if you remember, I also said that if you, in particular for the unconsolidated sand, is increasing the pore pressure, then it's moving in that. So increasing in pore pressure would move the point in that direction. So basically, that's the main effects that you should or hope to see in your seismic data if you have obtained the VP over VS and you have the acoustic impedance and you're just making a cross plot and you want to have some ideas of what is the difference in lithology, fluid, cementation, etc. between the various points, and you could use it.